dessert, which is network visualization. And so this is, for many of us, the reason we got into networks, or at least one of the first things that, maybe not the reason we got into it, but at least something that first captivated our imagination, was these kind of cool pictures, right? And if you find yourself in the consulting world or doing any of this kind of stuff, at some point in the day, someone's going to say, can you make me a network picture? That's kind of, there's a lot of that we end up doing. So if you're going to be in the business of making network pictures, at least have a little bit of idea about why you might do them and why they might be fun. So we're going to do a pretty quick version of why we make pictures and sort of how to make a good one from a bad one. Like many of these things we've done in this workshop, it's a lot easier to do something bad than it is to do something good. And the way we do something good is a little less instructive than the way you can do. So there's no actual formula. This is making pretty pictures is something almost realistically of an art over a lot of the other things. So networks have been found, or pictures have been foundational to networks from way back in the beginning. So the earliest sort of network-like images are coming out of kinship diagrams, and this is from 1871 in this case. There's also the other area where you see a lot of sort of diagrams a lot like this, or bureaucracies, right? So bureaucracies have been around forever, and so this is a good example of an organizational chart from 1921. But for many of us, the ones that are really sort of captivating came from Moreno's sociograms. And he has this wonderful book, Who Shall Survive, and a number of papers in the journal Sociometry, which have these images. And when you can kind of imagine when these things were first written, and as you read the descriptions of them, it really is this, like the first shot through a telescope or the first shot through a microscope. They're looking at this and they're just amazed at the extent to which they're seeing things that otherwise, and it's so clear that there's something else there that they wouldn't see otherwise. We're going to come back to this particular image quite a bit today as we sort of go through some various options. But he did it with all kinds of different elements. The place where I think a lot of these images, the original ones, really played very nicely was in community studies. And so the community study literature would send in teams of ethnographers into small towns, and they would try to ask people what's happening in those towns. This is Lundberg and Steele from 1938. And these images, this book is kind of incredible because all of these images that go off the page connect to another image on another page. So these things are actually very well done. And if you go through, you can see they have these sort of compiled edges where you're like this, M31 here is gaining all of the ties that are going off to another page. And if you read the book, you'll see that this is M31. So all of these ties here end up being connected to these sides. Those are those sets. So you could link these things across these different data sets. And there was an attempt to really document the social fabric of these communities in a way to try to understand, in this case, what the leadership structure of and what they came. This was a working steel town, and there was a very strong working class elite and a very strong working class and a very strong elite. But the city was being run by women, and so M31 was one of the, this Iron Lady of the town, and she organized everything else that was happening, and it sort of had this wonderful sort of sense that came out of the community study and became clear when you look at this kind of image. Quickly, though, people realized that once you have a little bit of an image, let's add more to it. And so there became this layering process where you're trying to add extra information. And so some of the early hand-drawn images were adding things like pie charts. So this was a neighborhood level map, effectively, of visits from one to the next. And the pie charts represent the extent to which people were coming from different places. Now, sadly, the network images sort of in contemporary world has been a little bit co-opted. So now we've come to think about viral marketing in this case. And this was literally a case where you're trying to use a network image to do something like show how to use hand lotion, if I remember correctly. And sometimes it's just like a complete, silly or almost dangerous. And so, and this is a case, this was a study of the conflict dynamics in the Afghan conflict. Put together by some folks at DOD or some consultants to DOD. And you might wonder what a quagmire looks like. There you go, right? So there's an image of it. And of course, you get downright spoofs of the real thing. So this is someone making a joke out of the Christakis and Fowler work about how your networks, how obesity is contagious. I still would love to know how someone managed to make, because if you look closely, like it's not just a random scattering of points. They actually did tie points together in here somehow. So I mean, someone spent a lot more time doing this than I would have imagined. But lest we think, right, that only journalists do bad network visualizations, the sad part is that bad network visualizations are ubiquitous in this field. So this is a published image in a journal. I don't remember which one I got it. I hid the names to protect the guilty. But it's a case that, you know, there's oftentimes people feel that they have to put a network image in, and just like whatever default shows up out of their screen, and they're using, they throw it in this set. And this one, you know, if you know something about the context, maybe you can tell a story, but it's certainly not compelling in itself. So what I like to do is figure out how you can, like what we hope to get out of a visualization. And a good visualization should be some kind of a gut check on the social reality you're trying to describe. It should communicate something that is intuitive and interesting and immediate and allows the authors and the readers to get something out of that image that would be harder to describe any other way. And so you've seen this diagram already a couple times throughout the course of this workshop, and people have picked up on it in many places because it's such a nice illustration of this conflict between racial integration and actual social integration, that we think we're doing everything right if we can get people integrated in the school door, but if the social networks are segregated, you've kind of lost the battle. And so that story pops out kind of nicely by just knowing what this image looks like. And so having that has been fairly compelling, and people have liked it. And so the question is, what is it sort of under the hood that makes a network compelling? And I have a whole sort of theory about how to do this well, but I want to just put a couple of ideas out there. One is that if you think about scatter plots, this is the classic series, each three of these scatter plots have the exact same regression fit, so you can fit the same lines, or the same slope, the same standard error, all that stuff to them. But the visualization tells you something that you wouldn't see from the regression summary statistics. And that's part of what a visualization does well. A visualization captures the gist of the whole thing in a way that a summary statistic does not. And it works in a scatter plot because the axes are meaningful. And so if you think about this particular element here, the y-axis and the x-axis, they're both ordered arrays. You have the exact same information if I just permute the x-axis, right? There's nothing inaccurate about this display of information. All the data points could be recovered, but it's not intuitive. It doesn't mean anything. And so the meaning of a scatter plot comes from the fact that the scatter plot has a fixed understanding of what the underlying space is. And so what I encourage us to do is make sure that we know what our underlying space is in a network. And sadly, we don't. And so in networks, any space goes. And that's kind of where you get these sort of crazy sort of fits across different sets. And these are all three images of the exact same network, all in the published literature of the Zachary Karate Club. And so some of these spaces, some of these underlying spaces, I would argue, are no different than a randomly permuted scatter plot. You don't get anything out of this image that wouldn't be better had by some of these other images. So if that's the case, what is the, I'm going to skip some of this, but what is that underlying space that we're trying to capture? There tends to be three underlying spaces that people tend to use. And there's a tree-based layout, a space-based layout, and a fixed coordinate layout. A tree-based layout, or some kind of a hierarchical layout, there's a fixed meaning to the y-axis. It's authority, or it's rank, or it's something. And then the x-axis is your free space to move. And that's used to essentially sort the lines to try to minimize crossing. And so whatever's going on of interest is on this y-axis, and we can say, you know, there's the general, there are the colonels, there are the majors, there are the captains, and there are the sergeants, right? So we have it down, we understand where it fits, and it works perfectly well. A force-based or a space-based layout is where you try to find a fixed length to the edge set, and you put nodes near each other if they are tied to each other, and they're far apart if they're not tied to each other. Now, some kinds of relations have an inherent ordering to them, and we should exploit that. So in a hierarchy, you want to put that so that the top nodes are at the top and the peripheral nodes are at the bottom, and take advantage of the flow of authority from top to bottom. Or you could flip it and go from bottom to top, or you could make it a circle from center to periphery. There's lots of ways to do that, but you have a meaning, an ordered meaning set, so use that to your advantage. It makes no sense to put that in a space-based layout. In a space-based layout, I can find the root of this tree if I look really close and find the node that has no incoming edges. But why make your audience do that, right? So don't force them to do something they don't have to. A space-based layout is best when you're trying to emphasize the clustering and the heterogeneities in the network. When you're trying to make sense of how this thing's not a single ordered, but there's different pockets in the network. Those pockets get turned into clumps or clusters in a space-based layout. So what you see in this case is that these nodes that have transitive closures, they're all going to be drawn into each other, whereas the nodes that they're not connected to or have these disconnected sets are going to be pushed out to the side. And so that sort of notion of a space-based versus a hierarchical layout is very useful for capturing that kind of social closure. Now I can do a tree-based layout on this kind of network, but it's noise. Like there's nothing there to be had that's of substantive use. Now the obvious choice, humans typically exist in spaces, is to think about a fixed coordinate system, and the classic fixed coordinate system is a map. This is a network of hospital exchanges. And so you can see major regional hospitals, like that's probably Bozeman. Bozeman sends out to Helena and some places in North Dakota, and there's Spokane, and so here's Seattle. And so you have these places, and a map works because we know the space, right? We know this geography, and I can point to where Denver is, and or Utah, and what have you. But this model doesn't particularly fit the data. And I had this little fit score I've introduced in the bottom. What the fit score is, it says if this model is working well, if it's working perfectly, then there ought to be a one-to-one correlation between the social distance and the physical distance. And so that would give you a correlation of 1. If the physical distance mapped onto the social distance perfectly, you would have a correlation of 1. And it turns out that those distances are easy to calculate, and so we can do that. And so the geographic case in this particular case has a correlation of about 0.5. So geography constrains the network, so it is positively correlated. But if I use a standard geometric or a space-based layout and let Fruchtem and Reingold put people near where they're at, you get a much better fit. And it's what you end up discovering is essentially Chicago, the sort of center Midwestern piece, actually pulls together the whole country in the middle, and you get those shortcuts between it. Now that fits better, but your audience knows what geography is, and so I would argue this is probably a better representation if you're trying to understand how hospitals are working. But once we have that fit model, we can think about it. Now another fixed coordinate is a circle. Circles tend to be useless, right? So a circle doesn't work very well by itself, and you can see it fits pretty poorly. The main thing a circle will do and circles were originally used when you were making sociograms by hand because A, it was easy to do, right? You can put nodes on a circle. And if you have a really small network, you can trace all of the lines and the tangents don't get hidden under the nodes. And in some cases, for really small networks, that might be useful. Now, one time I have found circles useful is when I let the whole network lay out as a space. This is, again, that hospital network. So I take that space-based layout and then a community detection on top of it. I cluster those, and then by taking a circle out of each one of those, I can see some extent to which there's density in the middle. There are other ways to do that, but that might be one reason you could defend it. People love these. I hate these. These are chord diagrams. Chord diagrams are the pie charts of the network world. Don't use them, all right? I can think of almost no reason to do it. I'm sure someone out there can find one for it. The main thing the reason that magazines and newspapers like them is because it's just so much color. It's like pop, right? But you can do better than that. You can save the color without the lack of any kind of flow information. So there's a whole thing here about distortion, but in the interest of getting you out of here, I'm not going to go through that too big. I'm going to focus instead on trying to solve a couple of problems. And so the first problem that we have is scale and density. And so this is that example I showed a couple of days ago about co-voting in the Senate. As a network, most of this information is completely redundant, right? In this case, a senator is a senator is a senator. What you really learn is that Democrats don't get along with Republicans. You don't need this element of information to get it. And in fact, you'd be better off probably looking at a heat map. So if you properly sort a heat map, you can extract from the sociogram and have much more information. And what you notice is that then these nodes in the middle that are not sort of swamped by these clusters become perhaps a little more apparent, and you can sort of interrogate that one way or another. The other thing you can do, this is the same graph that Tom showed a moment ago, is that you can instead look at a process on the network instead of the network itself. And so that we don't really care, if we really care about diffusion processes, let's look at the adoption curve as opposed to the network, and maybe you'll learn more about the underlying setting than you would from just the network itself. And I like doing the adoption curves from all possible networks. So let's imagine what the adoption, all adoption curves could look like on a network. This is your degree distribution right here. So this is the number of people who have ties, the number of people at each one-step distance, the number of people they could reach. Well, after a certain set of steps, you can see that some set of the nodes in this set, the bulk of diffusion would happen on that kind of a speed. But there are some places in this network that move really fast, others that would take a long time to go. It sort of gives you a sense, if a diffusion story is what you want to tell, this kind of a plot might be more useful. We've used these kind of tree-based structures to help highlight the importance of things like concurrency in the spread of disease through networks. In this case, we wanted to know how essential concurrency was for driving an HIV simulation. And what we discovered was that you could just plot whether the edge itself was concurrent. Maybe if you squint, you'll see a little more concurrency on the left or on the right there than you do on the left. But if instead you ask, where is concurrency upstream of me in the network? Then what you discover is that these big pieces require having concurrency upstream in order to open up the pieces downstream. And so it becomes immediately apparent that the path level concurrency is helping to drive the flow in these big spikes. We thought for a minute whether or not it'd be useful to add in the cross edges, the ones that didn't carry the simulation, but it seemed to just clutter the story, so we ended up not using it in the paper that we published. The second major problem then is dynamics. How do you display a dynamics on a network? The obvious choice is to animate, and so we have a whole paper on the way you might animate networks. I love network animation. I think it's really cool and fun to do, and Dan McFarland's data that Tom Wolf showed a few days ago, if I remember right, is a nice example of that. The one problem with animations is humans have pretty poor visual memory for movement, so we don't do a good job of being able to remember where things happen. So the kinds of questions that people can get out of this are really to help us see pace of change. And so if you think about what these networks are, this is again that sex network. What you're seeing here is that a lot of these relationships, the question was, who have you had a romantic relationship in the past, that's been ongoing in the past 6 months? A bunch of those relationships are really old. That's the ones you see sort of coming on here now. But then a lot of them, like these are adolescents. These relationships didn't last very long. Boom, boom, boom. They pop up there and they happen. And then the survey ends. And so it's not that everyone dies. They're just truncated. So it's not that there's a massive die-off in relationships, but we stopped collecting the data. So you want to be aware of that. You can take the qualitative version of Scott's Tergums and say, how do relationships change over time, and just plot the panels over themselves. And ghosting does a nice job of showing where the new relationships happen. So if you just go through the network, you can build it up one wave at a time. And we found that to be a pretty effective way, especially if people have it interactive so they can flip through it and see where the changes occur. The key to making this work is to effectively lay out the graph. Sorry, I'm in the wrong direction. Lay out the graph in its most dense. And then save those coordinates and stack on top as you go backwards. So essentially you build the visualization backwards from knowing the future to see what the past looks like. It's a little trick. Another way to do it is to use these things called multi-layer networks. And so we create a layer for each dynamic wave, and then we connect people to themselves through time. And so in this case, you're able to use the exact same space layout, and by weighting the within time edges much heavier than the between time edges, the networks almost always fan out temporally, because heavy weighted items within waves can't be connected to heavy weighted items in a next wave. And so the weak ties essentially implicitly order the spread over the time. And then you just have to rotate it to get it to be a sensible order. And so that's pretty nice. This is a split in a baboon troop, actually, over time. And so there's this one baboon that's holding together the set, if I remember correctly. I thought I skipped these. You saw this talk yesterday, so I'm not going to go through that. I'm going to end today because this is supposed to be the world's fastest thing, just to sensitize you to the art part of this. And so there's a certain scientific element of this, which is you need to make sure there's a data fidelity. You don't want to lie where you can. But you have enough space and freedom to try to figure out like how you make the choice. And so when we were writing the text, we were trying to figure out our visualization chapter. We thought, can we improve on some of the originals? And so like I love this graph. I thought it was really pretty. But it's not the most sort of informative network. You have to kind of read the ethnography to really see what's happening. And the first thing you need to know is that in the 1930s, when he was writing this, red meant positive. So red was good. It wasn't negative. We tend to think of a red tie as a bad thing. And so, in fact, the negative ties were in black and the positive ties were in red. And what's interesting, of course, is that CM here, everyone dislikes CM. So that's the central story of this particular network. And CM has one lonely reciprocal friend in the world. That's what this little X means. And the only other person that likes CM dislikes or likes CM's friend dislikes her. So you end up with this sort of centralized structure around this story of positive and negative ties. And the question is there some other hidden alliance structure built into this network? And so we thought for a while what would be the best way to display this network. And our original thought was to say, well, let's just see what happens when we use some modern layout techniques. And they're fine. It's not clear they do any better than the original. And they kind of end up with some stacking on top of each other that's not particularly nice. We do like the fact that you end up with, I kept the colors as the original just to make it comparative, but I do like the fact that you can sort of get a bit more of the sort of notion of these nodes on a periphery and a similar periphery. But again, this alliance structure idea is not quite there, so we wanted to see if there's something more we could do with that. So we thought, well, let's just try doing it by only taking positive ties as our source. That's the thing that is sort of the backbone of our network, and then layering over it negative ties. And so then we can at least compare the two to each other and see how one dislikes the other. But again, combined is kind of a mess. Right? It doesn't really work. So at this point we thought, well, maybe Moreno had it right. We should have just left well enough alone. And so we spent a lot of time thinking, well, we could perhaps do something that if it really is this sort of dislike of CM as our story, let's center the story around that and say, well, what is the sort of structure of dislike? So we just flipped the script there. We said, let's let the network lay out by the negative ties and then plot the positive ties over it. And what we discovered was that there's a community detection on top of it, that there are in fact 3 pretty nice bounded groups with a lot of positive internal ties and almost all negative ties between them, and then some sort of noisy nodes on the edge. And so what you end up with in this case is that this entire cabin, and that's what this is united in their dislike of this collector, which would otherwise be opposition between the set. So we were able to do a nice job, I think, of making a new story, and it pops out a little cleaner by focusing on this one element, which is the dislike of the central node. Now you'll notice what happened in the course of doing this, right? Is I've just told you, I've woven a story around this visualization because I read the case and we thought about it and we think this story fits, and I generated an image that fits the story I told. It was a reciprocal process of working on that. Some people would dislike that strategy, that it's somehow not scientific, that it's journalistic or some such. I think that one of the advantages of network visualization is that we're not lying about anything here, but we're using our own judgment to help inform what we're seeing. And once we realized that the negative ties were the story and allowed that to be the core thing that sort of centralized the image, we then layered the positive ties on top of it, and we got something that looked a lot like this. And then I went in by hand, and I just organized the groups to be a little more clear. And so for small networks, you can do that. You can go in by hand and do it. For really large networks, you need to do a little less of that, but it's just because it's not tenable to do. But I want to encourage you to have that kind of an approach to your visualization strategy, that what you're doing is you're trying to go in and tell a communicative story about your networks. You're trying to tell something that helps your readers understand what you see in the network. And we've done that now with sort of every sort of bit we do. I think this is an improvement. It lacks a certain historic, antique quality that I love about the original, but I think it sort of captures much more of the information and then a little bit more than we would have had originally. So That's what's there. And again, that's the world's way. If you go back in the notes, you'll see I have a much longer version of this, and I'd love to chat with you about the best strategies to get these things. One thing I will point out is that the distinction that you don't get to the last element here without going into something like Illustrator or some other your favorite graphics program and doing a fair amount of handwork. So that in order to get the coloring the way you want it, we deliberately decided to keep a font that's kind of similar to the handwritten ones, just as a nod to the historic set. So those kinds of elements, R is not going to do for you. So from an exploratory network analysis, where you're just trying to learn what the world is, it's best to keep an eye on these sort of notions of fit statistics and understanding where the network, how the network is represented on the page. And I think that's, I would stick with that as the thing you want to do. But when you move from exploratory analysis to presentation, take the time, once you've learned what the story of your network is, to make sure you communicate it and make the image worth the page space. And with that, I'm going to turn it over to Gabe, who's going to give you how to get some of this stuff out of R. And while he's switching over, I'm happy to answer any questions people have them. Please.
You mentioned not necessarily needing to put a full network and publish it because maybe to release too much data confidentiality. How would you go about the same process when doing partial?
Yeah. So in that case, what you want to do is figure out what part of the network do I need to show, or what simulated version from the network do I need to show, and then I would do the exact same kind of process. I would treat that new object that I've created as if it were real and do my best to show it. I think with fake data, the one thing that you can really do nicely is small multiples. So you can say, here's an ego network around a drug user, here's an ego network around one who has support, here's one who's experiencing homeless, and you can go through all those different features and be iconic about how you set it up.